Hello and welcome to my pre-recorded talk about rapid yet high-precision beam probing and targeting during optical bench construction. In the following, I will spare you from having to look at this corona-induced flood of hair, so let's get right to it. I'll first try to explain why we do the things we do, and then go on about how we actually do it. Alright. As you all know, LISA will contain some rather complex optical benches, which are built in a quasi-monolithic fashion to survive launch into space and to ensure the long-term interferometric phase stability required to observe low-frequency gravitational waves. Consequently, we use similar technology to test LISA's designated core components on ground. Some of these testbeds will be the subject of separate talks, and I'd like to encourage you to have a look at those as well. Shown here, for instance, is our TDOPS experiment. In many respects, building such an optical bench is a race against the clock. By that, I don't primarily mean the aspect of deadlines, but rather the building process itself requires us to be quick. Why is that? Well, in a nutshell, we use hydroxide catalysis bonding, optical contact bonding, UV adhesive bonding, or a combination thereof to place optical components, usually made of fused silica, onto a base plate of an ultra-low expansion glass ceramic. This has to be done with up to micrometer precision, and in most cases there is almost no margin of error, as this cannot be undone. So we have to get it right the first time. This process is often aided by and very much dependent on a coordinate measurement machine, or CMM, which uses a small spherical tip to mechanically probe workpieces in order to determine their geometry, position, and orientation in space. One usually starts off by probing the base plate, which is a rather lengthy process with a multitude of probe points to get a very precise and reproducible reading. The result is then used to establish a base coordinate system relative to which all subsequent measurements will be taken. Unfortunately, this base coordinate system is not magically attached to the base plate, and a real setup will always be subject to effects of thermal expansion, which are hard to control, and support equipment will often suffer from long-term mechanical creep. These aspects are especially relevant in the case of iterative processes, which alternate between partial measurement and readjustment. In the past, it has not been uncommon that we meticulously adjusted a certain aspect of an interferometer, only to find that meanwhile some other part of the puzzle has slowly drifted off, forcing us to start the whole process over again and again. So one of the lessons learned from this is that it's essential to reduce both the number of iterations as well as the time per step as much as possible. This is especially true when it comes to beam probing and targeting, for which a CMM can only indirectly be used. The basic principle to determine the position and orientation of a laser beam in space is to take two positional readings at different locations along the beam using quadrant photodiodes, or QPDs, embedded into a rigid structure which can then be probed by a CMM. Option number 1 is a sequential measurement using what we call a calibrated QPD singleton, or CQS. Such a device is nothing but a single QPD in a solid block of metal. Of course, you always have to minimize thermal expansion or compensate for it later on. Option number 2 is a so-called calibrated QPD pair, or CQP. As far as I'm aware of, this concept has originally been developed by the team at the University of Glasgow and combines a beam splitter and two QPDs into a single structure. Mounting such a device on a 6 degree of freedom parallel kinematics platform, better known as a Hexapod, results in an immense versatility and a large potential for automation. A pair of CQSs, on the other hand, uses up less space and is more flexible in some respects. For instance, they can be utilized in parallel on different output ports of an interferometer. Needless to say, the specimen in this image could be upgraded with computer-controllable piezo motors to gain the additional benefits of positional feedback loops and automation. Alright, for the readout of two QPDs in parallel, we use a custom-built 8-channel signal conditioning and analog-to-digital conversion board attached to an off-the-shelf Red Pitaya FPGA development board running a custom logic setup. The system is capable of operating in AC mode by driving a variable optical attenuator to impose an amplitude modulation onto the laser beam and by demodulating the measured signals accordingly, all efficiently implemented in synthesizable logic within the Red Pitaya's FPGA. From there, the digital signals are passed on to a custom Python program running on a PC, and this is what I'm going to show you now. The window pane is split into two sections dedicated to QPDs 1 and 2. Each of them has a tab for a positional readout of the laser beam on the QPD, utilizing differential power sensing. The readout is independent of laser power, and its intrinsic nonlinearity is compensated for by an inverse error function, resulting in a true positional readout. A crosshair is displayed to mark the average over a number of individual measurements. Configuration options include the creation and recall of QPD dark current calibration profiles, the control for custom amplification factors implemented in analog hardware on the ADC board, a switch between AC and DC operation, the beam's diameter incident on the QPD to adjust the positional readout accordingly, the ability to rotate and/or mirror the display, different visualization styles, and finally an auto-scaling system, which always keeps both the laser blob and the center of the QPD visible. The second tab shows the raw DC and demodulated AC signals, which is helpful for diagnostic purposes, and it also includes the ability to display the sum of the signals along with the maximum value reached so far, which is useful for quickly optimizing a free beam to fiber coupling efficiency. And finally, up here we have 5 buttons which let the user export measurement data, edit basic application settings, create and load analog front-end calibration profiles including offset and gain corrections, and control the laser's amplitude modulation along with the signal's demodulation. And the last button gives you access to the automation I mentioned before, as this controls the Hexapod underneath the CQP. This part is still heavily under development, and only half of the functionality has been implemented so far. Here you can configure the CQP's 2 possible input ports. You have the ability to lock the Hexapod's non-relevant degrees of freedom in order to maximize the range of the relevant ones. You can choose to control the Hexapod directly, or you may use these 2 joystick-like inputs to move only one QPD while the other one stays put. And last but not least, we're planning to include the option to automatically probe the diameter of a laser beam on a given QPD and to home in on a laser beam through the push of a button. Furthermore, a future upgrade to the system we are considering is the ability to measure the positions of 2 laser beams simultaneously on the same QPDs, which is helpful when aligning one laser beam to another. For this, the beams would need to have carrier frequencies far enough apart so as not to produce measurable beat notes, and our system would have to impose different AM frequencies onto the beams. However, at this point it is still unclear if we can squeeze a second set of signal processing pipelines into the Red Pitaya's FPGA. Additionally, we hope to be able to automatically interact with our CMM to eliminate numerous measurement steps which currently still have to be taken manually. And that brings me to the end of my presentation. I guess you can imagine that creating this combination of hardware and software was, and still is, quite a bit of work. However, I hope I was also able to convey the notion of how much we expect to benefit from it in terms of optical bench construction times in the future. Thank you very much for following me up to this point, and I'll be happy to try to answer any of your remaining questions. Bye.